So this is what I mean by other features. So we take a step back, switch the brain off, switch it back on, and now dig out some other data. So now what we want to do is we don't focus at the sea surface temperature. We now look at the temperature just above the seafloor on the continental shelf. And this is shown on the left side. And this is what Sam McClatchy, who was at SARDI in the past, has done. So he looked at the temperature distribution just above the seafloor. What he identified that in around springtime, before the summer season, there is a pool of relatively cold water located to the southwest of Kangaroo Island. See the blue water there, less than 14 degrees Celsius. That was based on relatively sparse field data. We know much more about this nowadays, okay? Because we learned that this pool actually contains very cold water, so it is actually the 12-degree Celsius water that we're looking after, but also high nutrient content. But it's concentrated within a very thin layer, so it's only a thickness of 10 meters or so, 10 to 50 meters, sitting on the seafloor. And this is actually what we believe the source of the upwelling, the source water that actually reaches the surface during upwelling event during summertime. So now a little bit more detail. How do you get that water there? How do you create this cold water? And that goes no further to some other mechanism, which is to do with so-called shelf break canyon or shelf incising canyons. And there's one which is called the Coedic Canyon, south of Kangaroo Island. It's shown here. And you can see it cuts through the shelf break. Yeah, there are other. These ones are actually the so-called Murray Canyons, the Murray Canyon group. This is where the Murray River ended in the past when the sea level was much lower. This is where the Murray Canyon ended. Again, there's still a signature of that, this canyon. It cuts through the shelf break. And I just want to show you some indications from a computer-based simulation that I did and some years back. And let's have a look at that. It's shown here on the next slide, and again shows you the near bottom temperature in a computer simulation. You can see the Kangaroo Island is situated here, and you start with a situation where you don't have any specific upwelling of this, where there is no Kangaroo Island pool. And then what you find out is actually that the canyon induces interaction between the Flinders Current and the canyon actually produces a localized flow near the bottom, injecting cold water and leading to the formation of this Kangaroo Island pool. Okay. All right, so that's the idea. So you might think of, well, I want to do something similar. I want to create now some technology to create upwelling in the ocean. So what I did is just in these little numbers here, I worked out here, if you have an upwelling event, how much volume of water is actually pumped into this area. And just estimating, just to give you an idea of how much water we're talking about. And this is just written here. So how much is that? The associated volume transport is about 0.1 million cubic meters per second. You can work that out from just knowing what is the transect area or the width and height of this flow and what is the speed of this. So what you need in order to create the Kangaroo Island pool is 100 million liters of water per second. Okay, so per day you need it's 8.6 trillion liters of water per day. Or if you have a 5-day upwelling event of over 5 days, you need this big number of water. So what I want to demonstrate to you is actually how massive the amount of volumes are that are actually transported through a submarine canyon. And it's hard to imagine the amount of nutrients that actually are brought into this. Okay, does that make sense? I hope so.